have a progress presentation by two of our master students, and they are both AI fellows, Canberk and Basit. So usually in our seminar series, we have an invited speaker who give a talk on a topic, but sometimes we want our students to do these so-called progress presentations to present their progress on their research project to get some feedback by us. And this is just one of those progress presentations. So as usual, let me start with introducing our speakers today. Again, Canberk and Basit. So they both received their bachelor's degree from Bilkent University in 2020. And we have been working together with Deniz Hoca, Erkut Hoca, and Duygu Ceylan from Adobe Research on language guided image editing. Just one of the tasks that lies at the intersection of computer vision and natural language processing. And today they will, their project, they have been working on this for about a year. They did a course project on my deep unsupervised learning course last semester, and we decided that it has matured enough to show you our initial results. Yeah, the stage is yours. I think you will start.
Okay. Yeah, okay. Hello, everyone. So I'm Basit, and I'll start our presentation. So we and Canberk have been working for a couple of months on it. So yeah, let's start. So our project is basically text-guided image manipulation using GAN Inversion. So since it is based on GANs, I'll start with the basic introduction on GANs. So I guess most of you have basic knowledge about GANs, but I'll just give some brief introduction about it. So the GANs, they are basically their training architecture is composed of two networks, a generator and a discriminator. So they are trained adversarially using a zero-sum game. Generator, as the name implies, it learns to generate new or fake data, and it has the same statistics as the training set it's trained on. And discriminator, it discriminates between the real or the generated data and fake or the real and the training set data and fake or the generated data. So these are the two networks that compete against each other and give feedback to each other to finally have a working generator that can produce realistic looking images. So we have this adversarial loss, this objective that the generator tries to minimize and the discriminator tries to maximize this objective. So yeah, I mean, these GANs, they have showed a lot of progress in the past few years, and in the 3-4 years, we have a lot of progress, such as there is an architecture called StyleGAN. StyleGAN architecture, it has progressed really good, and it can generate really realistic looking images. For example, on the right, you can see a lot of face images that look like real images. However, they have been generated by the StyleGAN network. So okay, we can generate images, but how do we have control over this generation? So this a typical GAN architecture, it takes latent code, random latent code Z, passes through a generator and outputs an image. But since it is random, a random latent code in a latent space, it corresponds to a random image in the image space. But we want to have some control so that we can produce some desired images. So to have that control, our approach basically solves that issue. But let's take a look at how StyleGAN inherently has some control in itself as well. So let's take a look at the StyleGAN architecture briefly and go over how it generates the images. So typically, GAN network initially, it used to be on only a latent code that used to pass through a series of convolutional layers and produce a final image. However, you can see there's not a lot of variation or control in this type of architecture. the latent code flows through a single pathway and just produces an image. But StyleGAN, it was really intuitive in this sense. It provides a better control. So in StyleGAN, there is a synthesis network G, which starts from a constant vector, and then this vector is passed through a series of convolutional layers to produce the image. However, on the way, the latent code is injected into the multiple stages using adaptive instance normalization. So it can be seen that the latent code, it's injected at different stages, and this provides a better control in terms of image generation and better training as well. So typically a StyleGAN architecture, it consists of 18 different stages. Each stage corresponds to different types of features. So initial features are linked to the coarse features, or like the like coarse features, and the middle stages are referring to some middle or like medium type of features, and the higher layers, that they are associated with more fine-grained features. So latent code is mapped through a linear transformation and injected into the network at different stages, and this allows for better control. So since we have this type of architecture, there is a thing called style mixing, which we can perform. So now, so we have okay, I'll move to this slide. So let's assume we have two different images, and we want to perform style mixing on them. So what it does is that it takes some of the styles. So from styles, I mean the intermediate latent code of one image. So we take some intermediate latent code from one image and some intermediate latent code from another image, and we then use them to generate the image, and this somehow takes some features from one image and some features from another image. So I mean, this since we have a lot of different stages in the StyleGAN network, we can control the features at different stages, like coarse styles, middle styles, and the fine-grained as well. So you can see the difference between different types of styles as well. So the coarse styles, it kind of associated with the face shape or pose, and the fine-tuned fine-grained styles is more associated with some colors, and the medium styles are associated with some mid-level facial features. So this is style mixing. This is some level of control that StyleGAN provides, but we want even more fine-grained control. For that, we propose our own architecture. So before that, let's take a look at the latent space as well. So recent works have shown that the latent space, it learned some disentangled semantics. So by that, I mean that by disentangled semantics, I mean that each direction in a latent code. So in a latent code, we can traverse in different directions. So it has been shown that different direction correspond to different characteristics in the image space. So one direction in a latent space, it maps to a specific feature in the image space. Also, so using this idea, we can actually control the generation of images in the image space. So we vary the latent code slightly, and it changes our image slightly while preserving the identity of the image. So this this idea is basically really important in image manipulation. So for example, if we take a look at this generation over here, we take a random latent code Z and generate an image using that. We have an image. Now, if we traverse in a direction N1, it is associated with a pose change, and it changes the pose of both of these images. If we take another direction N2 and change the latent code slightly, it changes the edge. So similarly, each direction changes a specific feature in the image while preserving the identity. The identity of the people remains the same. So this was about the latent space. Now, until now, I've talked about generation of images through a randomly sampled latent code. This is when you want to generate some random images and have some control over them. However, I mean, in real life or more practical application would be to have an image and be able to edit that image that we already have. So for that, there is the idea of GAN inversion. So GAN inversion is basically having an image and mapping it back to the latent space. So xreal is mapped to the latent space Z. So that is the inversion, GAN inversion. So there are three different methods of inversion. One is optimization based, one is learning based, and another one is the hybrid method. So optimization based method is simply taking a random, sampling a random latent code and producing an image, and then optimizing that by matching that generated image with the desired image until the latent code aligns with the uh, desired image. So this is the optimization based method, but it takes a few minutes, or depending on the number of iterations, it takes some time to actually come up with the inverted latent code. So to tackle that issue, there is a learning based invariant method as well, which actually trains an encoder that maps an image to the latent space. So this is a really fast method. It just takes one pass to generate the latent code. And then there is the hybrid approach as well, which uses an encoder to generate an initial latent code. And then you can perform optimization on that latent code to have more fine-tuned result for the latent code. So these are the three types of approaches. We will be using learning-based approach for our model. So as specified before, we want to have more fine-grained control. So we propose to have control using textual description. We want to control the image generation using text or natural language. So yeah, our input is an image and a textual description. Like over here, we give an input image and the textual description, and this together gives us a manipulated image. So it learns to understand the meaning of the text, and it preserves the identity of the image as well. So from a man, this image from a woman, this image converted to a man, and he got a beard as well. So these are the results from our model, by the way. So that is our motivation. So I'll be going over some of the related work. So again, this is one of the first models that we investigated while our research. So this model, it takes an image and text as well, and it passes both image and text through text and image encoders respectively, and combines them at different stages to finally produce an image. It consists of two different modules, a fine combination module and detailed correction module. So a fine combination module combines the image and text parts together, and then passes them on to the generator at multiple stages. And then detail correction modules completes the missing details in the generated image, and then finally gives us the desired image. So this was the GAN architecture, but then we move on to the CLIP model, or contrastive language image pre-training model. So this is one of the main models that we use actually in our approach. So this is a model that has been trained on a really large number of images and text pairs, about 400 million. So this model actually learns a joint embedding space for text and images. And using that, we can actually learn the similarity, find the similarity between an image and a random text prompt as well. So that is what we use to guide our as a guidance in our approach. So yeah, I mean, you can calculate the cosine distance between the image and text embeddings. So these image encoder gives us some image embeddings, text encoder gives us some text embeddings, and you can measure cosine similarity that actually gives us some kind of similarity in the actual sense, in the semantic sense as well. So this is a model that we use in our approach. Another model is StyleGAN, which is really close to our work as well. So this is an invariant based model like our approach. So invariant based model, in their invariant based model, they have two different approaches. So in the first approach, they actually learn joint or visual linguistic similarity space. So first of all, they have a GAN invariant model that inverts an image to the latent space. And they have a visual linguistic similarity module that actually maps the text to the same space as the image space. This latent space. So both image and text are mapped to the same space. So whenever we have an image that is inverted to the latent space and another text, we perform style mixing between these two different latent codes. So we have this latent code for image and one latent code for language, and they perform some kind of mixing to have joint representation for image and text, and that is then used to generate the image using a StyleGAN generator that contains information from both image and the text. So this is one of the approach that they use, and our approach is kind of similar to this one as well. Uh, so this is one approach, and another approach is optimization based. In this, they use an encoder to provide some initial latent code for an image. So this latent code corresponds to this image, and then they use the CLIP similarity. CLIP similarity, that is the cosine similarity that I talked about before, between the image and text encodings. So they use this CLIP similarity as a guide or a loss to optimize this latent code so that this image and this text prompt share some common semantics. And in the end, it produces, after some optimizations, it produces this image, which preserves the identity from this image and has some of the semantics from this image. So it removes the beard from this image. So this is the second optimization-based method from StyleGAN paper. Then there is another so StyleCLIP is also another paper that uses the CLIP model as its backbone as well. It is also an invariant-based model. So it has two approaches like the StyleGAN model. So the first approach is a direct optimization. In this approach, they like StyleGAN, they use a CLIP loss to optimize the latent code. And they optimize the latent code until the generation is actually corresponding to the text prompt. So this is one approach. And then another approach is the latent mapper approach. So first of all, in this approach, we map the image to a latent code using an invariant or encoder. And since we have this initial latent code, then they have this latent mappers. These latent mappers are actually used to predict some directions in the latent space that are corresponding to the changes in the original image. Now these latent mapper they are required to be trained on some text prompt, and using the CLIP loss, they are trained for a specific text prompt. For example, in this case, this latent mapper was trained on the text prompt surprised. So whenever we input an image to this network, it outputs such deltas that the generated image is always corresponding to a surprised person. So this is the second approach that the StyleCLIP proposed. Finally, we have another model that our approach is inspired from. So this is age transformation using a style-based regression model. In this approach, they are using, first of all, they are inverting the actual image using a PSP model, which I will talk about in the next slide. So they invert the image using an invariant model and obtain an initial latent code. And then they use another encoder model to obtain some residuals, which they add into this inverted latent code. And this corresponds to an age change in the latent code. So when we use this latent code to generate the image, it actually corresponds to the same person, but of a different age as specified here as alpha. So they concatenate this alpha as a separate channel in the input image. And this encoder is basically an age encoder, which is trained using different age regression age model. That age regression model is basically predicting the image of predicting the age of an image. So that is used as a guidance to train this encoder, and in the end, it is able to provide a guidance signal to this encoder, and we are able to learn shared space for age and images. So whenever we input an age, we can actually get the image corresponding to that age in the end. So this is one approach that we will be using in our model. Finally, we have the PSP model that we talked about. And the PSP is basically an invariant approach that we are using for our model. This PSP encoder is basically passing the image through a series of convolutional layers, and it takes some of the features from different stages, and then it uses them to map it to the latent code of the StyleGAN generator, and then that can be then used to generate the image after passing that latent code through the StyleGAN generator. So this is some of the related work for our approach. From here, Canberk will be taking over, and he will be talking about our approach and some of our experiments. So Canberk, the stage is yours.
Okay, so you can see my screen, right?
Yes.
So hello, I am Canberk, and yeah, we have been working on this project together with Basit for some time now. And now I will move on with the methodology and our experiments. So our architecture is inspired by the age transformation architecture Basit talked about. So that model mainly takes only the age, and you can manipulate only age, but we want to manipulate with a textual description. So let me go over this architecture briefly. So we want to do this manipulation through GAN inversion. So we are training encoders for this approach, and we have two encoders for this. So first one is the PSP encoder. This is a pre-trained network, so we don't train this, and it only takes the image as the input and outputs the latent codes for this image. So it doesn't take the text as the input. And then we have another encoder, which we call e-text here. So this time it takes the image together with some text embeddings coming from CLIP. And it uses these text embeddings at 3 different stages. I will talk in more detail about these. Then this encoder outputs some residuals. So the basic idea is here that if we can find some direction in the latent space, we can manipulate these images according to these texts. So we hope that our second encoder learns these residuals such that when we actually add these residuals to these latent codes and feed the final latent codes to the StyleGAN generator, we can obtain a manipulated image that is aligned with this textual description. So yeah, these residuals are added to the latent codes, and then we feed these final latent codes to the StyleGAN generator. And this is, again, a pre-trained network. We don't train this. So the only thing we train here is this e-text, the secondary encoder. And the text embeddings are coming from this CLIP model, which is, again, a pre-trained network. So let me now talk more about this part of our model. So as Basit talked about a little bit, CLIP is a model that is jointly trained with both text and images, and it can map them, it can embed them into the same space. So we wanted to utilize this. So you can actually find the cosine similarity of these embeddings. So to utilize this, we use the CLIP text encoder. So we first take our textual description and then feed it to this pre-trained CLIP text encoder model, which outputs a text features tensor. And yeah, this tensor has size n by 512. This n is the batch size here. And the next question is, how do we use these text features? So to do that, we are using adaptive instance normalization. So yeah, Basit already talked about adaptive instance normalization a little bit. This is initially used for style transfer in StyleGAN. So you have a style, you have a content that is manipulated by the style using a scale and shift parameters. So using this idea, we are taking these text features and passing this to an MLP called a mapping network to output scale and shift parameters. So this is called a mapping network because it's quite similar to the mapping network in the StyleGAN architecture. And this mapping network learns to output scale and shift parameters. These are initially channel-wise parameters that we spatially replicate to be the same size as the image features. And then the image features are first normalized and we multiply with the scale and shift parameters. So again, we are hoping that once we learn these scale and shift parameters, and once we modulate the image features using this text here, the new image features now are aligned with the textual description thanks to these text features coming from the CLIP embeddings. So where exactly do we use this adaptive instance normalization? So yeah, one thing I forgot to mention that this encoder shares almost the same architecture as this PSP encoder here. The only difference is we add some adaptive instance normalization layers at 3 different stages. So in the PSP architecture, they are extracting, after some convolutional layers, they are extracting some image features. These orange ones are for coarse, middle, and fine scale image features, which then are mapped to the latent codes here, then fed to the generator. So our idea is to manipulate these image features at 3 different stages, such that the image features are now aligned with the textual descriptions. So yeah, we don't do this on the right-hand side. We don't feed the latent codes directly to the generator, but let me go over here again. When we output from the encoder, we output residuals, and then first we add it to the original inverted latent codes, and then feed this to the StyleGAN generator to obtain this manipulated image. So to serve this purpose, we have 5 different losses. Let me start talking about the losses now. So first one is the L2 loss, which is a simple reconstruction loss. We use the pixel-wise difference for this. M here is our manipulation network. And second loss is the LPIPS loss. So this is a very similar loss. It's for perceptual similarities. And F here is a feature extractor, and we use AlexNet for this. So this is, again, both of these are for reconstruction purposes. And we have an important loss, the identity preservation loss. So ideally, when we manipulate the images using text descriptions, we want to keep the identity same as much as possible. So to serve this purpose, we have a pre-trained arc-based network, which can measure the identity similarities between 2 images. So we feed in our input image and the manipulated image to this, and we want to maximize the similarity, or equivalently, we want to minimize the distance between these 2 images to keep the identity as much as possible. And then we have a simple regularization loss that regularizes the latent codes. So this keeps their norm small, such that the quality of the generations are better. And then finally, and I guess most importantly, we have the CLIP loss. So this loss is the main loss that enables us to do these manipulations. So for this one, S here is the CLIP model that measures the CLIP similarity between a text and an image. So like I already talked about, the CLIP model maps both of these modalities into the same shared space. So in this shared space, it can measure the distance or similarity between them. So this S here is the CLIP similarity between the manipulated image and the text description. So we want to maximize the similarity, or again, equivalently, we want to minimize the distance between the image and the text in the clip space. So we are using this clip loss for that purpose. And one training detail, we are using a cycle consistency loss. So in each iteration, we have 2 passes. So in the first pass, we have, so we feed in the input image together with a mismatching caption. So this mismatching caption manipulates the image. And in the second pass, in the cyclic pass, we are inputting this manipulated image together with the original description that belongs to the input image here, such that we can recover and go back to the original image. So we go from original to manipulated and then go back to the original image. So yeah, that's it for our approach. Now I will move on to our experiments. Let me start with the dataset. So we use multimodal celebrity age group dataset. This is proposed by the authors of StyleGAN, and it consists of 30,000 images of celebrities, and it comes with 10 captions for each image. So in one instance, you can see on the right-hand side here, yeah, these 10 captions are fairly similar to each other. And then we perform multiple experiments, and we specifically experiment with the weight of the clip loss. And we compare with our errors results with StyleGAN model. So I will start by showing you some manipulation examples. So these results demonstrate the capabilities, the manipulation capabilities of our model. So first of all, you can see the text description is "she is smiling." So we can do gender changes with our model, and also our model is able to add smiles to the faces. And in the second example, you can see that the text description is "he has a goatee," so we can add facial hair as well. Moving on. Yeah, so this description says this person has gray hair, so we can manipulate the hair color using our model. Also, her mouth is slightly open, which is again present in this image, so we can manipulate the mouth as well. Next, we have she has black hair and is wearing lipstick and earrings, so we can again change the gender. We can add some makeup like the lipstick here. Also, our model is able to add some accessories like earrings here successfully. Yeah, and so moving on, we have this woman is chubby, so we can increase the chubbiness of a person here. And she wears a necklace. So again, we can add some accessories like the necklace around the neck. And finally, we have this example. She has straight and black hair. She is wearing lipstick and earrings. Again, we can manipulate the hair color. We can add some accessories. We can change the gender and add some makeup as well. So for all of these examples, our models work quite well. Now I will show comparisons with the StyleGAN model and also the GAN model Basit talked about. So yeah, so on the first image here, you can see is the original one. On the left column, we have the GAN manipulations, and then we have two manipulations for StyleGAN. First one is for their visual linguistic similarity model. So for this one, they learn their own text encoder, and StyleGAN B is where they optimize the latent code with the clip loss. And then on the right-hand side here, you can see our results. And inside the parentheses is the weight of the clip loss. So we experimented with different ones. We start from 1.0, 1.5, 2.0, and 2.5. So one thing to observe here is if we go from lower weight to higher weight for the clip loss, the changes that we describe here become more apparent in the images. Like if you compare the hair color here with of this one to this one is changes the hair color more, but it comes with the cost of manipulating the identity as well. So the identity is changed too much compared to the model here. So also, if we increase the weight of the clip loss, sometimes there are some unwanted changes that we didn't describe. So in both of these outputs, we have his mouth open, which we didn't describe in this text description. So yeah, sometimes the model, most of the time it works quite well, but sometimes there are some unwanted changes or some changes are ignored by the model. But overall, I could say that the model, all of these models were quite well in manipulating the hair color, especially compared to the clip-based model of StyleGAN, which didn't really change the hair color that much. And we can move on to these results. So in this description, she has oval face and long black hair. So like I said, sometimes some inputs are ignored, like this long hair. Our model didn't add the long hair. And also, again, we didn't specify that she has her mouth open, but yeah, if we increase the clip weight, sometimes there are unwanted changes. And she is wearing earrings, is apparent in all of these images. So our model is very successful in adding accessories like that. And like I already discussed, if we increase the if we increase the clip weight loss, identity changes quite a lot. And actually, you can observe observe these two images on the bottom here. They are both clip-based models, so the identities are quite similar to each other in these both of these images. Actually, compared to original, they look more like each other. So you can see the effect of the clip loss on these manipulations here. So for this model as well, the text caption is "He has no beard." First three models are quite well for us, but then the model with 2.5 doesn't really like remove the beard. And for these images, the StyleGAN model works quite well. And so here's an example our model where our model works quite well. This old woman has big lips, pale skin, and gray hair. So big lips, all of these models can add quite well, and gray hair, and especially this old woman here is apparent in our last image here. So there are some wrinkles in the face, like I don't know if you can see, but yeah, our model can also manipulate age as well, and it's like better than some of these models here. By the way, this GAN model is not able to produce some high quality, high resolution images. So that's why they are kind of a bit blurry here. And then, yeah, another example, our model works quite well here is this one. So this woman wears earrings, she has oval face and high bones, she's smiling. So most of these are apparent in all of our models. And yeah, we can successfully manipulate the gender. We can add, again, earrings and smile to the face better than our baseline models. And yeah, so here's another challenging example for our models. Eyeglasses are, as we observed, are like quite challenging, and none of these actually models can able to add eyeglasses, but only the model with clip weight 2.5 can add eyeglasses here. But yeah, again, it somehow changes the identity more than the other models. So these are the comparisons with the StyleGAN, and I will show one comparison with the StyleCLIP model as well. So StyleCLIP is not exactly a fair comparison right now because so the text input here is curly hair, and then they train a specific mapper for this text input. So they can't really input any custom text. They need to train for a specific text input for this curly hair. And yeah, on the middle, you can see the results of StyleCLIP. But like our model still is able to manipulate using this textual description as well. Like we can add curly hair to these faces. And actually our model also stays true to the original hair length more than the StyleCLIP as well. Yeah, those are for the visual comparisons. So we have some quantitative comparisons as well. So for this purpose, we use the CLIP similarity. So this is the average CLIP similarity between the text and the image. But again, this is not really the best metric to compare these models, because all of these models are like directly optimizing this metric. So we need to, like, we are in also search for some better metrics to compare these manipulations with. So if you have some ideas, please like share with us. So yeah, if we increase the clip weight, obviously the similarity, clip similarity increases, and it's quite similar to the StyleGAN clip optimization based model, which is higher right now. But this is for a portion of the validation set. So we are not able to check this clip similarity for all of the images in the validation set yet, because an important note to discuss here is this clip optimization based model of StyleGAN takes quite a bit of time, because it needs to optimize for each instance, for each image, and it takes quite a long time to validate for the whole data, for a whole validation set. But for our models, we can generate our manipulations instantly. So that's one plus side for us. And actually, we can reach similarity scores close to the clip, close to the StyleGAN model if we increase the clip weight. So I mean, that's not really, I guess, like I talked about, a great metric to compare these results. So yeah, let me go into future directions and conclusion now. So currently we are experimenting with adapter layers on generator. So let me show you on this figure. Right now our StyleGAN generator is not text-based, so it takes only the latent codes, and it produces the output, and it is completely fixed, it's completely frozen. But we are looking for ways to adapt this generator as well to our purposes. So our idea was to add adaptive instance normalization layers as well, like we added in the encoder, to this StyleGAN generator, and train only those layers while keeping the other layers fixed. So currently we are experimenting with this. It's not working quite well, but we are trying to debug this. And in this approach, we are using the CLIPS text embeddings again to feed into the generator, and the adaptive instance normalization layers are used to manipulate, to modulate these image features in the generator. And different from the adaptive layers in the encoder, we are using a control variable that controls the amount of blending. So this time we start with 0. So the zeros means it starts with the original generator, and over time we hope that this control variable learns the amount of blending of the old image features and the newly modulated image features. So yeah, currently we are working on this idea to improve our generations. And for conclusions, yeah, I would say that our model works quite well for most of the manipulations. And like I already talked about, we observed that the weight of clip loss has a big impact on the performance of our model. So again, we are still trying different hyperparameters for this, especially for the clip loss and for the identity loss. We need to find the right balance such that we can apply these manipulations, and we can keep the identity as much as possible. So yeah, also one final note: once we finish, we will also be doing a user study for quantitative analysis of our models. So in this user study, we will present the users with our manipulated images together with StyleGANs and like any other baselines, and then we will ask the users which one is more accurate with the textual description. And we will also ask for the realism as well. So we will ask which image looks more realistic which generated image more realistic among our model and the baselines. So yeah, that's it from us. Thank you very much for your time.
Yeah,
Do you
thank
have
you,
any questions?
Canberk. Thank you, Basit. Yeah, we are open to your feedback. Any questions, comments, suggestions? So maybe I can jump in and say a few words, at least my own take on the comparison with the current state of the art. So as you have seen, the only existing method, and that's actually quite recent. I think you didn't mention the date. It was just out this summer, while we have already started working on this project. And the GAN approach is, so here, one thing we didn't do yet is time comparisons, right, Canberk? So maybe you can say also a few words in terms of the computational efficiency. So I suppose, like especially the StyleGAN approach uses some sort of optimization. So ideally, optimization-based approaches are better. But of course, since they use backpropagation to perform this editing process, they are quite slow. So one thing we want to achieve here is somehow have the a similar generalization capability in terms of the custom textual descriptions, and also to have visual quality compared to this model. And TEDGAN also uses this frozen generator network. So like Canberk have mentioned at the end, one thing we actually really want to try out is to include these additional layers while keeping the generator still fixed. We will be only training these extra layers. And there are not that many studies that tried that. And let me also say that not this one, but in some cases, you also can witness the disadvantage of using a pre-trained network. So since that generator network is trained to generate certain images, it may not encode all the possible input images you can think of. So there is also a trade-off between this reconstruction quality and what kind of images, like if you input an out-of-domain input image, like for example, the person is in a relatively strange pose. Of course, all of these methods, they may fail miserably. And that is basically because the generator part is frozen. So that's why we want to explore that option. Yeah, Osman.
Yeah, you mentioned the cyclic loss that you were using. So you first generate a image that fits the description that you used, using, like, you use clip loss there to train that. And then you, like an autoencoder, you try to reverse this, right?
Yes.
So what is the effect of this?
So,
like, why do you do this?
Okay, maybe I can clarify certain things before answering your question. So here, during the training process, you don't have ground truth manipulation results. You only have certain images with the correct descriptions. Okay. So the training process, somehow using the other images, the captions of the other images in the sampled batch, you basically generate those target descriptions randomly. And there are some certain ways, like using the clip loss to measure how well is your manipulation results. However, that clip loss is does not that much look at the original input image. So with this cyclic consistency, we want to have the adaptability that if we take one image and change it according to a description, can we go back to the original image using the original description? So that's only for improving the robustness of the method.
I was just like, I would have liked to see like some images that were just, you know, like they were trained just using that clip loss and not this reconstruction loss.
Okay.
Are there any like papers that have done this that I can check? Like
yes, some I don't exactly recall. Maybe
I understand the effect that this would have, but like it would have been nice to see it in practice actually. Like how much effect does it have?
Yeah, of course. Yeah, we should definitely do an ablation study to check the effects of these different components. Yeah, you are absolutely right.
Thank you. Thank you for the presentation as well.
Thank you.
Ilker has a question about so instead of adaptive instance normalization, have you tried film instead?
Yeah, we haven't tried different approaches actually. So we our first idea was to use this adaptive instance normalization, and it worked quite well. So we didn't really try many things for this. I guess, yeah, we can take a note of that and try that. So thank you for your suggestion.
Then what do you think about how does it compare with the adaptive instance normalization?
So I don't really know the details of film right now.
Actually, I don't know the details about the adaptive instance normalization, so I was curious about this.
Yeah, it is almost like the same thing with a different name, Ilker. So they were proposed by different groups, but at its core, it only performs some sort of an affine transformation. So it's quite similar to film.
Okay.
Okay, any other comments?
Have you tried the model with your own images, Canberk Basit?
I actually tried a while ago, so I guess it worked to some extent. Maybe my face was kind of out of domain, maybe. So that's why it didn't preserve the identity as much, but yeah, I tried it, but I don't have the images saved right now.
By the way, you mentioned that you were trying to inject some embeddings to your pre-trained network, right?
The generator, right?
We tried something like that in another task, and it failed. But if you make it happen, then let me know.
Okay, I'll let you know.
So if there are no other questions, let's thank our speakers once again. And I strongly encourage the other graduate students to give these type of progress presentations. Like yeah, today we have seen many nice feedback from you. So I strongly suggest the others to do these progress presentations in
Hocam,
our seminars. Yeah, okay.
a last comment from me. I think this architecture is similar to our architecture in some way. Maybe we can combine ideas or
yeah, we can talk more on this together. You can just yesterday we were talking about the cyclic consistency loss, for example.
yes.
And there are quite similarities in the details. Yeah, of course. Okay, okay, everyone. Thanks again, and see you next week. I guess next week we are meeting in Tuesday evening instead of the morning. Okay, then see you all and have a nice week.